Hello everyone, my name is Bao Haishen and my supervisor is Professor Liu Longquan. We are from Shanghai Jiao Tong University, which is located in Shanghai, China. Today, my speech topic is a new composite metal joint and its structural performance. I've divided my topic into these three parts. In engineering, because of technology limitation and different uses, we will not manufacture an airplane or rocket as a whole, which is unrealistic and uneconomical. We will divide the structure into individual components and connect the components with fasteners or adhesive layers. The picture on the left shows the rear edge compartment bracket of aircraft, which use high-load lock screw to connect the braked ribs and beams. The picture on the right shows the composite material shell of a rocket engine, which use adhesive to connect the composite material and the metal structure. To connect metals and composites, we need a joint method. There are three joint methods to connect metals and composite. There are mechanical ways like bolt, bonded ways, and hybrid ways. For different ways has their disadvantages and advantages. It has high reliability and high weight for mechanical joints. It has low weight but low reliability for bonded joint, and it has high cost, high weight, difficult to improve the strength for hybrid joints. A considerable number of researchers have been conducted to develop the strengthening and toughening technology of adhesively bonded joint. Huang et al. Used soft inclusion to improve the mechanical property of adhesive layer. As shown in the figure, soft inclusion can induce the crack deflection. The Welding Institute (TWI) developed the commeld joining method for composite metal structure, which produces short pins by cold metal transfer method on joint area of the metallic structure and increase the load capacity and energy absorption of the joint significantly. And T et al. To slow or stop the crack growth in adhesive by introduce dark line thermoplast between brittle epoxy adhesive just like this. Here we proposed a novel joining method between metallic and composite structure to enhance the mechanical performance of metal composite hybrid structure. The mechanism of a proposed joint is to arrest the crack in bonded line by some thin pins running through the thickness of joint plant in bonding area. This picture is our adhesive multiple pins joint. The upper plant is a composite plant. The bottom one is a metallic one. The adhesive bonded is the middle. There are rows of metal pins punched in composite and metal and connect them together. Here is our specimen manufacturing method. We use template with design holes to locate the pins between metal and composite plates. As shown in these three figures, the part 1 is a composite material. 5 and 6 are template with holes. Part 9 is the metal pins. Part 7 is the bolts for fixed to templates. Part 8 is the gasket for grip. The geometry features of the specimen are in accordance with the American Society for Testing and Material Standard. Dimensions of the two constituting plant are the same: 100 plus 25 plus 3 mm in length, width, and thickness. The length of the facing zone is 20 mm. There are 15 pins, 3 rows, and 5 columns running through the joint's planned in facing zone. The row distance P is 3 mm, and the column distance S is 5 mm. The diameter of the pin is 0.8 mm. There is adhesive on the surface of the pin, and thus the pins are bonded together with a metallic and composite joint plant after the adhesive is cured. The left picture shows a group of adhesive multiple pins jointed specimen. The right one is a group of conventional adhesive joint specimen. Quasi-static experiment was conducted for all group of specimen. One tab in dimension of 25 plus 25 plus 3 mm in length, width, thickness was attached on each side of the specimen for grip. Quasi-static test was carried out on servo-hydraulic universal testing machine of type MTS E45.105 in accordance with ASTM D5868 standard. The related load of the testing machine is 40 kN with a measure error less than 0.1%. The test was set in displacement control and loading rate was 0.2 mm per meter. This two pictures showed the displacement versus load curves result. Conventional adhesive joint and adhesive multiple pin joint specimen. Overall, the load displacement result of the specimen was with the same configuration has a rather good consistency. The reinforcement increased the load capacity and energy absorption of the adhesive joint significantly. Comparing with the joint without reinforcement, the joint with reinforcement behaves a certain extent of plastic deformation before they reach their peak load. Compare the tensile deformation and other characteristics of this two structure. Compared to our novel adhesive multiple pins jointed structure, the peak load of a conventional adhesive joint decreased by 90.9 to 22.8%, whereas the total energy absorption decreased by about 35.2 to 45.0% respectively. The effect of the disbond on both of the load capacity and the fracture energy in joint with reinforcement are lower than this without reinforcement. This indicates that the penetrative reinforcement decreases the sensitivity of the static strength. The failure mode of a novel hybrid joint is not like traditional adhesive joint breaks suddenly. It has experienced partial debonding, large area debonding, and mechanical leader pulling out. The sudden failure of traditional bonded structure is caused by debonding of the metal and the composite plant, as shown in the upper figure. The higher failure load and higher failure strain exhibited by the novel structure are not only caused by debonding, but also bending and pulling out of the metal needle. FEA model of the pinned joint with and without debonding without debonding was developed using Abacus software, which is shown in the figure. Longitudinal tensile load was applied on the joint similar as the test. 8-node liner brick element was used to simulate the planes. A layer of COH3D8 with a thickness of 0.1 mm was used to simulate the bonded relationship between composite and metallic. As for the model of the joint with through thickness reinforcement, the steel pins was modeled as C3D8R element. A bilinear traction separation law was used to define the constitutive response of cohesive element. The damage factor SDEG was used to characterize the failure index of the cohesive element. The comparison of the relationship load versus displacement are shown in the figure. The solid line represents the experimental result, and the dotted line represents the FEA simulation result, from which it can be seen that the simulation result has a good consistency with the test result. This indicates that our simulation is good enough. Here is the failure mode of the adhesive or conventional bonded joint. With displacement increase, the stress of the adhesive bond or cohesive element is increased. When the load is 4.1 kN, most of the cohesive element is under failure. When the displacement is 0.45 mm, nearly all of the cohesive element is under failure. Debonded phenomena happened. Here, this picture shows a failure process of adhesive, or called our novel joint. The cylinders represent the metal pins. From figures, we can see that just like the conventional joint, when the displacement go to 0.59 mm, almost half of the cohesive element is under failure. When the displacement go to 1.51 mm, almost all of the cohesive element is under failure. And when the displacement go to 5 mm, all of the cohesive element is under failure, but the metal pins and the cohesive elements around the attached the metal cylinders are still can bear the load, transfer the load. Let's do a conclusion. First, a novel joining method between metallic and composite material was presented and compared with adhesive joint. The joining reinforced by metal pin improved the ultra failure load. Moreover, it increased the failure strain and energy absorption capacity much more. Furthermore, the novel joining method decreased the suddenness of failure of the joint. Second, there is a bridging force between pins passing through the planes, so that the pins not only inhibit the adhesive zone on facing surface from pinning, but also transfer load together with the adhesive layer on the facing surface. Therefore, the presence of the pins increases the load capacity and the energy absorbing capacity of the joint. Thanks for listening.